Well, greetings out there in YouTube land, and welcome to today's video in which we will delve into the mysteries of isolation transformers. In this video, rather than theory as was presented in part 1, we're going to actually get into practical creation of our own isolation transformer and comparing it to the performance and safety provided by a much more expensive commercial isolation transformer. Using some of the contributions from Patreon patrons and PayPal donators, I bought a pair of 4 amp transformers. These are 120 to 12, 120 to 12. And I'm going to try to connect them sort of tail to tail, just like we did in the Ricktone power supply video where we made the Tremolo boost, and see if we can't end up with a decent isolation transformer, in this case for a little over $30, and that included shipping and all. Now, since most of the amplifiers I work on have 2 amp or lower fuses, I figured that 4 amp transformers would be able to provide a reliable source of current to those circuits that I'm testing without stressing the transformers or causing them to overheat. One concern I had was that I know there'll be a voltage drop across each of these transformers. Will the output voltage be too low to power a normal amplifier? Now, since receptacle voltages have gone up in the United States to around 120 volts, some slight reduction down to like 110 or 115 might actually be beneficial. But if it drops way down like around 90 or so, I don't think it's going to be usable. So there's only one way to really find out, and that is let's assemble these together and make our own isolation transformer. Okay, using the color coding that was provided by the supplier of the transformers, I've connected I have here the primary will be energized with 120 volts AC. I tied off the center taps and insulated the ends so that keep them out of trouble. And we connected the 12 volt output from this one to the 12 volt input of the second transformer. And then we have the output voltage from the primary of this transformer. Okay, I also have my AC voltmeter connected across the terminal, so when we plug in the primary to this transformer, we'll see how many AC volts are being applied to it. It looks like 119.1 is the input voltage. I've also taped a piece of paper here so that I can write down every one of the measurements for future reference. Now let's see what kind of no-load output we get when I plug into the current limiter. Well, actually not too bad. 116.7 or 0.8, which is still higher than the 115 volts that we used to get from the receptacle. Now granted, that is no load voltage. Once we start running current through this, the voltage level will probably go down. But for now, I'm pretty happy that the voltage drop across the 2 transformers is not all that great. And now for our test circuit, I'm going to use a really nice original Gretsch 6150 amp. This one still has the original 2-prong plug, and I believe the death capacitor is still in circuit. Ooh. So this should be a perfect candidate then for us to test our isolation transformer. Okay, I've turned the little Gretsch amp around. I pulled that rear cover off so that we can gain access to the circuit. This is an ideal type of amp for this purpose because we don't have to pull the whole chassis to gain access to the circuit. Just remove that back panel. And sure enough, there is the death capacitor. Oh, I touch it and the light goes out. The death capacitor is in place in this amp. Okay, here's the plan. I have the original 2-prong plug that I'm going to connect to the output of the homemade isolation transformer. Remember, we've got now around 116 volts with no load at these terminals. Let's plug in the isolation transformer, turn on the amp, and see if we have enough current and voltage for it to operate. Now with the amp off, we're showing 117.3 volts AC at the plug of the amp. I think once we turn on the amp, that voltage is going to drop. Let's see if we still have enough voltage and current for the amp to operate. Okay, I turned on the amp and the voltage dropped dramatically, and it's only come up to 85 volts. I'm not sure if it's going to operate at that voltage level. Let's crank up the volume and see if we... Seems to be working. Okay, I've got another idea. Let's check the plate voltage with this plugged in to the wall outlet, and then we'll check the plate voltage with it plugged in to the isolation transformer. Let's see if the plate voltage drops way too much for us to be able to operate and reliably test this circuit. Okay, I have the test probes from pin 3 to pin 8, that's plate to cathode, and with the isolation transformer providing the current, the plate voltage is only 162 volts DC. Alright, I plugged in the amplifier directly to the current limiter, and we see now that the plate voltage has gone way up to 268.5, which is the normal level for the plate voltage in this amp. So there was about a 100 volt drop on plate voltage because of the restriction put in the line by these two transformers. Even though they're both 4 amp, wired like this to be an isolation transformer, they simply cannot provide the current and voltage necessary to operate even a basic 3-tube amp. So I think you can save yourself the time, trouble, and money of trying to build your own isolation transformer using transformers like this. One alternative you might consider is to get a single 1-to-1 transformer that can handle, say, 4 amps. If you can find one on eBay or something like that, that might work, but this arrangement is not. But fear not, I more or less anticipated the results of that first experiment, but I just had to see it for myself. Now that I have, it's time to move on to our second alternative, which I've gotten for us, and that is a medical grade isolation transformer. Here's Jack's new buddy, a little feral cat we've named Ollie, who lives in our backyard now and begs for food and catnip. He keeps Jack very entertained, and for that we're appreciative. After Ollie finishes his morning bath, we'll see if he enjoys some of Jack's boutique catnip. And as you will see, Ollie loves his catnip. Roll in that catnip, Ollie. He's hooked. Well, Jack enjoys Ollie's shameless performance. And this is the time we need to discuss something of great importance, and that is that not all isolation transformers are equal. Okay, there are two main types, medical grade and tech grade isolation transformers. Now, another name for the medical grade could be non-tech grade or public isolation transformers. Now, most medical grade isolation transformers, the word isolation does not mean what we think it does. It means that it is used to eliminate background noise, electrical interference, and things like that so that very delicate medical instruments like EEGs and EKGs can operate without any sort of problems that can be caused by external electrical noise. Well, that's all just fine and dandy, but it doesn't work for us because that type of medical grade isolation transformer will have an internal connection between the neutral return line and ground. Okay, that will make it not suitable for our use with our oscilloscopes. Fortunately, however, that problem can be easily remedied. So you can convert a medical grade isolation transformer that is really for isolation from electrical noise into a tech grade isolation transformer that effectively isolates you from ground reference. Now, part of the reason I bought this isolation transformer is in the ad I could read this statement: output floating, neutral conductor not grounded. That means that even though this is called a medical grade isolation transformer, it really is a tech grade transformer. I will not have to modify it. However, I'm going to open it up and show you if you have a real medical grade isolation transformer that is not for isolation from ground reference. I'm going to show you when we open it up how you can modify it and make it suitable for that purpose. Before I pull the lid, let's see where this one came from. It's the Toroid Corporation of Maryland. Okay, with that in mind, let's pull the lid and see what awaits us inside. And what lurks within is the biggest, fattest toroid transformer I've ever seen in my life. Okay, now surely this gem is going to be able to adequately power any amplifier that we're going to encounter that draws up to 5 amps of current. Now there's a piece of protective tape here. I'm going to pull it back to show you where if your medical grade transformer is not suitable for isolation from ground reference, where yours will be different from this one. And that is right here is the neutral line. It's usually white and the hot line is black. In this, the hot is brown and the neutral or return is sort of a yellowish color. Somewhere in your medical grade isolation transformer, there will be a connection between the neutral return and ground. If that exists, then remove it. You see that doesn't exist in this one. You want to make yours like this, with no ground connection between the neutral return and somewhere on the chassis it'll be bolted down. Okay, so that's how you can salvage your medical grade isolation transformer and turn it into a tech grade one like this. The second characteristic which must be discussed is, if you look in here, there are 3 dark green grounding lines, and green is the normal color for grounds. There's one for each bank of output receptacles, and there's one from the grounding lug down here on the power cord that we're going to plug in to a wall receptacle. Now all 3 of those are combined right down here and bolted to the chassis of this unit. What this means is, when you plug in your amplifier or whatever you want to test to this outlet, you're going to get a ground reference to the chassis of that amplifier from this bottom lug, which is continuous with this bottom lug, which goes directly to the grounding lug in your wall socket. Now the result of that is debated widely on the internet and is a huge source of confusion to people with regard to isolation transformers. We're going to put that to rest with some very clear and straightforward statements about the effects of this grounding lug. I'm going to discuss with you the effects of leaving this in place and using it on the amplifier that we're going to be testing, or if you choose to go inside and eliminate the ground connections for your output receptacles, or using some sort of an adapter which turns a 3-prong outlet into a 2-prong outlet. Okay, we'll discuss all of that. Just be patient. Let's briefly discuss these weird receptacles, and you may encounter them also if you buy a medical grade isolation transformer. Normal plugs, of course, are not going to work with this. Now, when I bought this, I saw these, and the vendor agreed to send me 3 cords that have a plug at this end that will plug into this weird outlet, and at the other end would be a female normal AC outlet. Okay, but he forgot to send them, okay, which is always fun. They're on their way to me now, but I didn't want to delay the video, so what I did was I made my own. I removed this from an old computer, cut off all the wings and extensions and the ways that it used to bolt into the chassis. Okay, I left the 3 wires intact, hot, neutral or return, and ground. And now this will fit in here very nicely and plug in and allow us to use and test our isolation transformer. So I just wanted you to understand what this weird thing is sticking out here, okay? But it's going to really make it easier for us to demonstrate how this thing works. Fortunately, he did remember to send me the power cord for the unit, so I plugged one in here, and as you can see, the other end is very conventional, and I'm going to plug that into an AC outlet. Okay, let's discuss now how this thing works. I've connected the black hot wire to a light bulb socket and the white return wire. Let's flip on the isolation transformer and see that yes, it works just like we would expect when something is connected in this manner. Okay, now let's try a little experiment. I'm going to disconnect the common return from the bulb, and I'm going to touch it over here to what amounts to the ground lug of the AC receptacle in my shop. I put a stainless steel sheet metal screw into the ground lug hole, and I've connected this jumper to it. So that tip right there is equivalent to the ground or earth ground in my receptacle. Now, if this output right here from this receptacle has ground reference, me touching this to ground will illuminate the bulb. Let's see what happens. Okay, I've touched it. Nothing. Okay, our receptacles at this point from this unit have no ground reference. Okay, and I've proven that by touching this to the ground lug of my wall receptacle. Now, what would have happened if you had left your return wire on your medical grade isolation transformer connected to ground? Okay, if you had the type of isolation transformer that's really just to isolate from electrical noise, not from ground reference, if you touch it to this piece of metal, it would illuminate the bulb. So my suggestion is, if you're not sure about your isolation transformer, test it this way and see if you touch the metal here that is the ground lug of the AC receptacle and this lights, you're going to have to go into your isolation transformer and unground that common return wire. However, since this particular medical isolation transformer has the output floating, neutral conductor not grounded, I don't have to do that. It's already been done on this one at the factory, so we can move on now to step 2. Now, for testing purposes, I'm going to use a really nice, completely original Gretsch 6150 amp. Okay, this one's so original that it still has the two-prong power cord. This is going to serve us well here in our demonstration of the difference between a grounded chassis and a non-grounded chassis. This is, at this moment, an ungrounded chassis, okay? There is no 3-wire power cord. Now, as you can see, I've connected the two-prong plug for the Gretsch amp to the black and white wires coming from the isolation transformer. The ground wire is not connected to anything, all right? Nor is the chassis grounded at the moment. Step one, let's turn it on and see what our plate voltage is when the isolation transformer is providing the voltage and current, to make sure that the isolation transformer is adequate to power this amp. We know darn well it is, but let's prove it right now. Okay, I have my multimeter set to DC voltage. I have the probes connected to pin 3, which is the plate, and pin 8, which is the cathode of the 6V6 output tube. This is just like I did yesterday. Let's turn it on, and then come over here and see what the plate voltage is. Now, when I tested the amp plugged into the wall outlet, the plate voltage was 268 volts DC. It appears that using the isolation transformer, it's actually higher. It's around 278 volts. So it's gained 10 volts of plate voltage by the using the isolation transformer, which tells us that the winding ratio is probably not exactly 1-to-1, but it's real close. Regardless, we know now that our amp can be adequately powered by our isolation transformer, unlike the two smaller transformers in the first experiment. Now let's see if this circuit is actually isolated from ground reference. In other words, if we were to think of this clip right here as the ground clip of the oscilloscope, and it's equivalent to it because, as we saw, it goes back here and connects to the ground lug of the AC outlet, which is exactly what the chassis and ground lug in our oscilloscope do. So we'll be thinking of this then as the ground lug of the oscilloscope. Is there any potential now between it and any point in here in the chassis? In other words, is the circuit adequately isolated? Then I can take my ground lug from my oscilloscope and touch it to any place in the circuit. Well, let's find out. Now, instead of measuring voltage potential between different points in the chassis and the ground clip of my oscilloscope, I'm going to measure current flow. Okay, and the reason being is you can get false readings if you measure voltage potential. There are things called ghost potentials, ghost voltage readings, where it's actually due to capacitance within the transformer, and it might say 60 volts or 70 volts, but it is unable to flow any current. The ghost readings are kind of annoying, but they have to be eliminated. To eliminate them, I'm going to measure current flow between the points in the circuit and the ground clip of the oscilloscope, because that's really what causes the damage. It isn't the voltage, it's the idea of current flowing through my oscilloscope probe and the chassis of the oscilloscope. So I have hooked up my digital multimeter here to show us if microamps of current will flow between different points here in my amp circuit and my oscilloscope ground clip. Okay, a microamp is so low that it's almost well, it's virtually indistinguishable from no flow, okay? So let's see if we can get any microamps to flow between the circuit and our ground clip. Okay, for our first test, let's hook on here to this lug, which is bolted right to the chassis of the amp. Okay, and let's see if any current will flow between the chassis and the ground clip of our oscilloscope. And we see that it's 0 microamps. Now I'll just move down to some random point here. Okay, I don't know what that wire goes to. It's hot, I'll guarantee you, but this is the same as if you were moving your ground clip around in the chassis and you touch it to that point. Is there going to be an issue? Well, no, 0 microamps. Okay, let's come over here to some other place. Let's look at the cathode. Okay, we know that that has a little bit of voltage. Is that going to flow to our oscilloscope? Nope. Okay, 0. Let's go in here and connect, oh heck, let's go for broke and connect to the AC primary. Okay, that's the tail of the fuse. AC primary, surely that's going to flow some, okay? Nope. 0 microamps. So in other words, the way we have this set up right now, with the 2-prong plug plugged into the isolation transformer, there's no place in this chassis or circuit that you can connect the ground clip of your oscilloscope and have any problems at all. Because no matter where you clip it, even to the primary winding of the AC, no current is going to flow. Now, for those of you skeptics who are saying, well, wait a minute, that's a DC ammeter. It can't tell if there's any current flowing between the primary circuit here and my ground clip on my oscilloscope. Well, then let's change the meter to AC volts. How about if I show you 0.004 volts potential between the primary circuit and the ground clip of my oscilloscope? How about those apples? I just thought of one connection that might really make an impression on you, and that is, let's connect to the plate of the 6V6. For God's sake, that's the high voltage, is it not? What is that, close to 300 volts? Surely that's going to flow through my ground clip and to my oscilloscope? Nope. Absolutely no current flow whatsoever, even if I hook the ground clip of my oscilloscope to the plate of my output tube. Now there's 2 points I have to make here, okay, and these are critical for your safety, so listen up. The moment that I connect that ground clip from my oscilloscope to any point in the circuit, it's safe, okay? No current is going to flow through my oscilloscope and harm my probes or my scope. But I have now given ground reference to the circuit. Now think about that. I have done the unthinkable by hooking that clip in. Yes, I can put the clip anywhere I want, but the second I do put it in, suddenly that is ground for this circuit and it has ground reference. How does that affect us? Well, 2 ways. Number one, you can no longer touch anything in here because it has ground reference and it can pass through you to ground if you're grounded and kill you. So when you're putting your ground clip in, be very careful, because the moment you attach it to any metal in here, this circuit becomes ground referenced and can kill you. So be very careful. Number 2, if you have 2 probes, as I do, you cannot connect the ground clip from one probe, say here, and the other clip for the ground clip for the probe anywhere else, because then you'll have 2 ground references and current will flow between them and through your scope and possibly destroy it. So once you've put a 1 ground clip from your oscilloscope probe anywhere in here, number 1, we can't touch any metal. Number two, the next ground clip that we put in for our second probe has to be exactly the same spot that we hooked the first one, or else we're going to have a potential between them which could effectively fry our probes and our oscilloscope. So please remember those two rules. They are critical. Now let's move, I think, to the final point that we have to make. And that is, and this one is debated widely, should we ground the chassis of the electronic device that we're testing? In other words, should I, when I plug the device in, should I plug in a two-prong plug like I just did, or should I plug in the three-prong plug from the device? Well, let's see what happens. Okay, if we jumper from here to the chassis of the amplifier circuit, which is exactly what would happen if you had a three-wire plug, right? Isn't the green wire bolted to the chassis? It would come over here and plug in right down here, and it would connect to that point. So let's do it and see how it changes things. Okay, here we go. I've installed a jumper between the grounding lug of the isolation transformer receptacle and the chassis of the amplifier. Now this is exactly the same as if we now had a three-wire chassis grounding power cord being plugged in to that receptacle. Now I'm going to be using DC volts as my criteria of judgment if a potential exists, simply because I don't want to take a risk of damaging my meter by exposing it to a high flow of current. Okay, so we'll be measuring volts of potential between different places, locations in the circuit, and the grounding clip of our oscilloscope. And I can assure you that any potentials we encounter will not be ghost voltages, but will be the real thing. Okay, our first point in the circuit that we'll check will be the ground lug here that goes to the chassis. Okay, so you're figuring, well, there shouldn't be any potential because we got chassis, same thing, right? Except it shows a tiny bit, 0.1 millivolts of potential. Now what that reflects is this: the connection between this lug and the chassis is not perfect. Apparently there's a tiny bit of resistance between the lug and the chassis, and that tiny bit of resistance is reflected in this voltage drop from this lead to this. But I will say that 0.1 millivolts is essentially zero, so we have no problems here connecting our ground clip on our oscilloscope to that lug. But let's move down the line a little bit here and connect to that same place that I connected before that showed zero current flow when I had an ungrounded chassis. And oh my Lord, I now have 211.6 volts. And God knows how much current that would be flowing through my oscilloscope ground clip if I had foolishly connected it right there with a grounded chassis. Okay, let's disconnect it there and come down to the lowly cathode. Okay, now that, surely there can't be a lot of voltage potential. Well, there is, 14.3 some odd volts, which means a little bit of current flowing through our oscilloscope ground clip and through the chassis of our oscilloscope. I don't know if that's enough to do any harm. But let's go and clip on to the plate of the 6V6 and see what happens. Well, the amp didn't like it, and neither did our oscilloscope ground lead, because it now is facing 284 volts, and God knows how much current is coursing through our little ground clip from our probe, causing probably a whole bunch of harm to the probe and maybe the oscilloscope. So as you can see, there's only one place in the entire chassis that we can now connect without just burning up our probe or oscilloscope, and that is the chassis itself. So as you can see, there is a huge difference between plugging in the electronic device with a 3-wire chassis grounding cord into your isolation transformer or using a 2-wire cord. With the 3-wire cord, the ground reference is the chassis, and you cannot connect your oscilloscope ground lead anywhere in here without destroying the probe or the scope, except for the chassis itself. Now, if you're willing to let the chassis float and use a 2-wire cord to connect this circuit, you can go in with your oscilloscope ground lead and connect any place in the chassis without a concern. Okay, and once you've connected, we know then concern begins. Can't touch, you can't touch metal, and if you hook another oscilloscope ground clip up, it has to be to exactly the same spot. But you have much greater safety and freedom of choice if you do not ground the chassis of the device that you are testing. Okay, I think it's time to bring this rather lengthy and complicated video to a conclusion, and I think the best way to do it is to review the safe rules for proper use of an isolation transformer with an oscilloscope. I think it's important to emphasize that these rules were derived by experimentation. As I showed you in the video, these are not simply my opinion or some hearsay that I got off the internet. Every one of these statements is backed up by a demonstration within the video. Rule number 1, the chassis of the device under test must be ungrounded. If you are one of those individuals who refuses to work on any device that doesn't have a grounded chassis, then that's fine, but you're wasting your time by using an isolation transformer. The minute you ground the chassis, you're losing any benefit that would have been derived from the isolation transformer. Now, this was well demonstrated in the video where I showed you that an ungrounded chassis, none of the points within the circuit had any potential to earth ground, and therefore could not harm your oscilloscope or probes. The minute that a ground was provided to the chassis, all that changed, and the circuit went back to having all of its normal operating voltages and presenting once again a very serious hazard to both you and the oscilloscope and probes. Now, if you have a 3-prong plug on the device that you're going to test, you have to either use a 3 to 2 prong adapter that has the polarized 2 prongs on one side, 3 receptacle holes on the other, and no connection between the ground lug and the receptacle in the isolation transformer. Or, if you don't like using adapters, you can permanently disconnect the output receptacle grounds in the isolation transformer if you wish. In that case, you'll have to go inside and find the 2 green wires which provide the grounding to your output receptacles. Trace them all the way down to the floor where they're bolted down here to the chassis ground. Unscrew the nut, remove the 2 of them, tape them off, curl them up so they're out of harm's way, and then tighten that nut back down on the power cord ground, which you will leave intact. Rule number 2. Once you have plugged the device under test into an isolation transformer that meets all the criteria described in the video, and the chassis is ungrounded, then you are free to attach your first oscilloscope ground clip anywhere in the circuit. Because, as was shown in the video, no point in the circuit, if this criteria is met, will present any sort of current flow capability that can harm your probe, you, or the oscilloscope. Okay, so you can attach that first ground clip anywhere, but once you have attached that first ground clip, everything changes. The circuit now has ground reference, which means it's gone back to presenting a shock hazard to you, so you have to be very careful, especially if you're grounded in any way, and for heaven's sakes, you wouldn't be, I hope, you wouldn't be so foolish as to be grounded while working on electronic gear. But you have to be really careful. This is the one-hand rule, okay? You can go into that chassis with one hand and not touch any metal. B, once you have attached a single ground clip and you recognize that a shock hazard's been created, the second probe ground clip that you attach has to be to exactly the same spot in the circuit as the first clip, and I mean exactly the same spot, or else you'll create two different ground references within the circuit, and therefore you may have potential between the two ground references, and that could create a hazardous situation for the probes, the oscilloscope, and for you. Well, that's about it for this rather lengthy video. I want to thank the Patreon patrons and PayPal contributors for helping me finance projects like this, which provide learning to all viewers. Any viewers that would like to join in with your generous brothers and become donators or patrons, I will include links in the video description to help you do so. Meanwhile, I think that's it for us right now. I hope this has been a very helpful video and that you'll join me for more in the